Ladies and gentlemen, good evening. My name is Charles Draper. I am the chairman of the Herschel Society. Welcome to the 2024 Caroline Herschel Prize Lecture given by Dr. Héloïse Stevance of Oxford University. The Caroline Herschel Prize Lecture was established in 2018 by our society in association with the RAS to celebrate Caroline's memory by supporting promising female astronomers early in their careers. It's now in its 7th year. I'm very grateful to many people for allowing this to happen. Professor Fran Baganel of the University of Colorado in Boulder made a major donation to enable it to be funded. The Royal Astronomical Society, as associates, and practical help in making it work. I'm very glad that Dr. Andy Young is here today, and he'll say a few words about that shortly. Professor Mike Edmonds, who's here, who is an ex-RAS president and our vice president, was very helpful to me in setting it up in the first place. So, Mike, thank you for that. And Professor Paula Chadwick of the University of Durham, who I hope we'll hear from shortly, and their colleagues on the panel. They had the task of selecting this year's winner. And finally, the University of Bath for hosting the event. So why celebrate Caroline Herschel? Caroline was born, like her elder brother, William, in Hanover in the mid-18th century. Unlike him, she was given little education and was destined to life at home of domestic drudgery. William became a successful musician in Bath in the 1770s, and he brought Caroline here, both for his sake and for hers. There, she became in turn an effective housekeeper, talented singer, and tireless observing assistant. Fame from the discovery of Uranus took them both to Slough in the 1780s and with close contact with the King's Court. Important visitors in astronomy filled their days and nights. Caroline was increasingly recognised as an astronomer in her own right and received a pension from the King as the first paid female astronomer. William's marriage caused some upset, but more opportunities for Caroline to make her own observations herself, including 8 comets and several deep sky objects. Most importantly, William Caroline's system of communicating and recording their observations pointed the way for astronomers after them up to the present day. Caroline returned to Hanover after William's death and carried on cataloguing the night sky, partly to support her nephew John Herschel's observations. These were precursors of the new general catalogue of deep sky objects that we all still use today. She was awarded the RAS Gold Medal in 1828 and many other honours subsequently. She made a real mark in an age where women in science were almost unknown. No wonder she is such an inspiration for so many today. Indeed, the UK and German governments established another prize in her name in 2021. This is the Caroline Herschel Medal, and this is awarded each year to a UK or German-based established woman astronomer. So there are 2 prizes in Caroline's name. So I'll now hand over to Andy Young to say a few words on behalf of the RAS.
Great, thank you. It's an honour and privilege to be here to represent the Royal Astronomical Society. The RAS was founded in 1820 to encourage and promote the study of astronomy, solar system science, geophysics, and closely related disciplines. The RAS does many things, including organising scientific meetings, publishing research journals, maintaining an extensive library, and supporting education and outreach activities. It also recognises outstanding achievements by the award of medals and prizes, which is why we're here today. As you just heard, the Caroline Herschel Prize Lectureship was established in 2018 by the Herschel Society in association with the RAS to celebrate Caroline's memory by supporting promising women astronomers early in their careers. And the RAS is proud to support and showcase the scientific achievements of women astronomers who are role models for others. I apologise for almost being late today. I tried to use AI to find Bath in my car and I almost failed. And I'm looking forward to the professional. I'm really looking forward to hearing about artificial intelligence, exploding stars and hungry black holes.
Now I hope Paula Chadwick can now say a few words.
So I'm sorry I can't be with you. Durham's quite a long way from Bath, and as I'm currently head of department in Durham, my time is not always entirely my own, I'm afraid. So it falls to me just to give you a little bit of background to this lecture. As I'm sure we're aware, women have made great strides in science over the last few decades, but there's still work to be done. In 2024, the Institute of Physics noted that physics is the 15th most popular subject amongst girls, with only around 23% of girls taking physics at A level, while it's the second most popular subject for boys. And their research shows that too many girls and other young people from underrepresented groups are put off by outdated stereotypes. They don't think that the world of physical sciences is for them. The Caroline Herschel Prize Lectureship is one of the ways we can show that whoever you are, wherever you come from, physics and astronomy can be for you. The lectureship supports promising women astronomers early in their careers. The intention is to give early career women extra visibility, to break down those stereotypes, and to provide a stepping stone to an academic career. The awardee must not, at the time of application, hold a permanent academic position, although on occasion awardees have gained such a position very shortly after being awarded the lectureship, so it obviously works. We had an exceptional field of candidates this year. I and the other panel members, Jane Birkby and Lindsay Fletcher, to whom enormous thanks, really had a very difficult time choosing our lecturer for 2024. So this year's lecturer really is the best of the best. So Héloïse is a computational astronomer and Schmidt Artificial Intelligence in Science Fellow. She's based at the University of Oxford. She's developing artificial intelligence models for international sky surveys. The tool she's designed will work alongside experts to find new cosmic explosions that can teach us about the origin of the elements, black hole physics, and the expansion of the universe, from stars exploding to stars being eaten by black holes. It's a pretty rough time for the stars. In the coming year, the Vera Rubin Observatory will start observations, and that will lead to an absolute deluge of data, and humans alone will not be able to process that in good time. So we wait to be fascinated by what Héloïse has to tell us. Thank you, Charles.
Paula, thank you. So I now invite Dr. Héloïse Stevance to give the 2024 Caroline Herschel Prize Lecture.
So thank you very much, first of all, for the prize and for inviting me here. Now, to do astronomy, you don't need fancy equipment. People successfully sailed the Pacific using nothing but their eyes and the motions of the stars and what they knew of the night sky. But new technology can really help you open a new window onto our universe. The invention of the telescope allowed Galileo to find the moons of Jupiter. The invention of photography put astronomy into the Industrial Revolution. And I learned today how John Herschel helped with photography. Unfortunately, not soon enough for me to put him on the slide. The later part of the 20th century also brought new materials like semiconductors, which allow us to control the flow of electricity on a really small scale. That allows computer scientists to turn computers from things that take up a whole room to things that fit on a desk. It also allows us to turn photons into electrons, to turn light into electricity, so the digital camera. The other thing that happened in the late 20th century is rocketry, which means that we could send artificial satellites out into space, including telescopes. Now, that's very useful if you're an astronomer, because the atmosphere is a big, beautiful blanket that protects us from some of the harshest radiation in the universe. But it also makes us blind to some really interesting colors, and it gives us a bit of a blurry view of the universe. I think one of the standout pictures of the early 21st century is from the Hubble Space Telescope, showing us how much better we can see the night sky out into space. The Hubble Deep Field, which I'm sure you've all seen, this is only a very small zoomed in, cropped out version of the Hubble Deep Field, is a very small area of the sky, 10 times smaller than the moon. And that area of the sky was observed by Hubble for 1 million seconds. Now, this zoomed in, it's a shame we've got the lights. Oh, I highly recommend downloading the full picture on Wikipedia and zooming in on your phone. You can see so many galaxies. This picture is maybe 100 times smaller than the moon. And there's maybe 100, 200 galaxies on here alone. Now, the tradition of deep fields has stood the test of time. James Webb Space Telescope was launched on Christmas Day 2021, and in 2022, it released its very first deep field. Now, in this picture, you can also see some really cool galaxies. See that one? It's really stretchy because there's a big galaxy cluster between us and the source of the light of that galaxy, and that's bending the light around the gravitational well. Now you can see a few stars as well, the famous 6 spikes of James Webb, and also an awful lot of galaxies. Now, the point of this introduction was partially to have an excuse to show you some of the prettiest pictures of the universe that we have. But it was also to really impress upon you the fact that the history of discovery in astronomy is the history of a partnership between researchers and their machines, between astronomers and new technologies. And that's the theme I really want to explore today. Now, with my job, I'm very fortunate that I get to travel quite a lot. Earlier this year, back in June, I was in Chile to observe at Héloïse Observatory for a couple of days with the new technology telescope. That's the tin can you can see in this picture. Now, I'm not sure whether you can see with the light, but that sky has a lot of clouds in it. Not ideal if you're trying to observe. Now, fortunately for me, the clouds were swept away very quickly by extremely strong winds that started battering the summit. The very strong winds meant that it was impossible to open the telescope without damaging it, which meant I had a lot of time at night to twiddle my thumbs and play with my phone. And so I took this picture of the night sky with this very phone. Now you might be able to distinguish the shape of the Milky Way. You can see the center of the galaxy shining bright here, and you can see a few clouds as well. These clouds are clouds in the galaxy. They're clouds of dust and very, very cold gas that obscure our view. Now here is a slightly nicer picture of the Milky Way taken by a proper astrophotographer. You can see some actual proper colors, and here you can see a fuzzy thing there. That is the Large Magellanic Cloud, our nearest galaxy. Now, if you've ever gone to a dark sky area to observe with your own eyes, you will know that the night sky does not look like this. Not to our eyes. You can't see that many colors. You can't see that many stars. If you look at a truly dark sky with your eyes, you'll maybe see a few thousand stars. When we observe with the telescopes that we use, so even more powerful than the cameras that took these pictures, they can see 1 billion sources in the night sky. Now, it's very difficult to picture 1 billion of anything, but I'm going to try to give you a sense for that order of magnitude, because we're going to use big numbers today. So a few thousand seconds is the time that this talk will take. This talk is 3,600 seconds. 1 million seconds is over 11 days. 1 billion seconds is nearly 32 years. So the sky is big. It's really, really big. I can't emphasize this enough. And not only is it big, it's always changing. Many of the stars that we can see in the night sky have varying brightnesses. Even some of the very well-known ones, like Betelgeuse, the shoulder of Orion, has a brightness that fluctuates very regularly. Occasionally, it has a great dimming event in 2019 to keep astronomers on their toes. But there's also stuff very nearby that can keep our sky interesting, like asteroids and comets. Here you've got a picture of the comet that was visible at dusk back in October. Here I've got a GIF of a very unusual view of an asteroid. That's an asteroid being, the moon of an asteroid actually, being shot at by a spaceship on purpose, I might add. They did mean to do that. They crashed the spaceship onto a moonlet to see what impact it would have on that asteroid. And you can see the ejector happening there. Whoop, that's nice. Now, on top of variable stars, asteroids, and comets, there's a lot of other things that can happen in the night sky, a lot of explosions in particular. The explosions are the things I care about. Now, some of these things we're going to have time to mention today. Some of these we're not. What I really want you to focus on in this slide is the kind of timescales I've written on here. So hours, days, days, weeks, minutes, hours. Those are the kind of timescales on which these objects evolve significantly. These are the kind of timescales on which you want to take new pictures so you can study them, so you can understand them and do science. And these timescales are quite short. That means that if you want to do a good job, you have to survey the sky not only across space, but across time. You have to survey it over and over and over again. And that's the kind of capability that astronomers have only begun to have in the 21st century. Now, the telescope sky survey I'm going to talk about today and focus on in Atlas, because that's the one I work with. But there's others, and there's other coming surveys like LSST, like the Vera Rubin Observatory. But today, I'm going to focus on Atlas, the Asteroid Terrestrial Impact Last Alert System. Now, Atlas is funded by NASA to find and track near-Earth asteroids, particularly the ones that could be dangerous for life as we know it. In order to do that, Atlas has 4 telescopes scattered across the world, 2 in the Northern Hemisphere, in Hawaii, and 2 in the Southern Hemisphere, 1 in South Africa, 1 in Chile. This gives it a 360 view, nearly 360 view of the night sky. Now, because we want to take pictures very often, and we want to go back to the same patch of sky very often, having a 360 view is not enough. You need to be able to take pictures quickly enough. And to do this, Atlas has a very large field of view. Now, you might be able to distinguish on this screenshot of one of our dashboards, the pictures that were most recently taken by Atlas. You can see them here. Now, remember the deep fields that I was showing you earlier, maybe the pictures I was showing you were maybe 100 times smaller than the moon. On these pictures, the moon is like this big. You can fit the moon many, many, many times in an Atlas field of view. You can see here how it tiles up the night sky. And it means that our telescopes can go back to the same patch of sky every 24 to 48 hours. That gives us the cadence that we need to study near-Earth asteroids, and also to find the things I care about, the things that go bang. Now, I could spend a whole hour talking about nothing but explosions and the many ways that stars die in very dramatic ways, but we don't have time for this today. So I'm going to give you a brief overview of 3 of my favorite types of explosions. The first one that we're going to talk about is probably the most well-known, the supernova explosion. Now, supernova explosions, we've known about them. They were discovered in 1930, very early 1930s, and astronomers spent the next 100 years inventing dozens of subclassifications. We're not going to go over these today. We're going to talk about 2 main classes of supernovae, the low mass star supernovae, the high mass star supernovae. The low mass stars supernovae happen when a star like the sun dies, and it turns into an object called a white dwarf. It's about the size of the Earth, but half the mass of the sun. The Earth is 100 times smaller than the sun, so it's very dense, a very compact object made of mostly carbon and oxygen. White dwarfs have a very interesting characteristic. If you make them too heavy, they explode. If you make them 1.4 times the mass of the sun, they explode. So if they get too close to a companion and merge with it, or just suck up its outer envelope, they go bang. And when they go bang, they create most of the iron in the universe. So just a quick reminder, the universe was born with just hydrogen, helium, a little bit of deuterium and beryllium. So everything around you, everything that you're made of, most of the things that you're made of, created in stars or in explosions of stars. The other cool characteristic of these types of supernovae is that they can help us track the expansion of the universe. I'm not going to expand on it today, haha, but no, never mind, okay. But some people got a nifty little Nobel Prize in 2011 for this, so good for them. My favorite type of supernova is the high mass star supernova. That's what happens when a star born with more than 8 times the mass of the sun reaches the end of its life. At that point, its core collapses into either a neutron star or black hole. The rest of the star explodes, it gets really bright, and creates a whole bunch of oxygen, calcium, and other things that your body is made of. Now, the neutron star is the very exciting bit, in my opinion. This picture, I should say, is a real image. It's a combination of 5 images from 5 different wavelengths from different observatories. It's not CGI, it's not AI, this is a real picture. That's why people spend billions of dollars for a picture like this. The purple/pink thing is the X-rays, the same X-rays that allow doctors to see your bones. These were observed with Chandra Space Observatory, and you can actually see the neutron star there. And the reason there's a little pinwheel nebula around it is because that neutron star is on steroids, spinning really quickly and launching a jet. So yeah, the high mass star supernovae are definitely the coolest. Now, the neutron stars can have a second part to their lives once they've been created in supernovae, and they can explode again as kilonova explosions. Now, this is an artist impression. We've never gotten that close. Kilonovae are neutron star mergers, or sometimes a neutron star gets eaten by a black hole, but mostly neutron star mergers. And they happen because stars, and massive stars especially, are often born with a friend. They're often in binary systems. And so if you've got 2 massive stars in a binary system, once they've exploded and turned into neutron stars, you've got 2 neutron stars in a binary system. And neutron stars are wacky objects. They are literally the densest thing that is not a black hole. So they do interesting things to the fabric of space-time. Now, a quick reminder, the fabric of space-time can be pictured as a literal piece of fabric. It's a 2-dimensional approximation to 3/4D system, but it works well enough. And anything with a mass creates a well in the fabric of space-time. So you could put a very heavy ball bearing, it's going to make a well. If you throw a coin, it's going to spin around and fall in the well. That's the concept. But if you've got 2 very dense objects next to each other, the well that they're going to create is not going to be spherical, it's going to be sort of peanut-shaped. And when that spins around, because the whole system spins around, it's going to wobble the fabric of space-time and is going to send waves going through the fabric of space-time. Now we're going to do something very dangerous, people. We're going to try to play a video. Okay, let's try this. Click. Right, in this video, you can see gravitational waves, hopefully, yes, because they are distorting the fabric of space-time and the light from the background. As those waves are being produced, they take energy away from the system, which brings the black hole and neutron star closer and closer and closer and closer together until eventually they merge. They merge. They merge. There we go. They merge. And then the ripples start to fade away. Very nice. That worked. Okay, now let's take a look at what happens with 2 neutron stars. In this case, yes, you can click. In this case, we're not going to be able to visualize the gravitational waves, but we can see what happens to the material of the 2 neutron stars. Now, these 2 neutron stars are going to get squished as they get really close to each other. They're going to get squished and distorted by their own gravitational field, which means that some of the material is going to merge and some of it is going to get shot out, literally flying out into space, and it's going to form this ejector and this disk around the hypermassive neutron star, which is eventually going to collapse to a black hole. You're going to see it 1, 2, 3, bam. There we go, black hole. These systems and this ejector is what shines so bright. That's what we can see from these distant galaxies across space and time. And these ejecta are also made of very weird neutron-rich material, and they're able to create some very heavy elements like platinum, palladium, gold, rare earth elements, all of the good rare stuff that you need to make smartphones and other pieces of technology. Now, the final type of transit we're going to talk about is where the hungry black holes of the title really pays off. Those are the tidal disruption events. Tidal disruption events are what happens when a black hole is minding its own business and then a star comes in and ruins its day or makes its day, depending on what kind of narrative you put on this. So we're going to once again have a lovely video that I did not make. Click, please. Awesome. You're going to be able to see, we've got a black hole, kind of like interstellar. They don't all look like this, but that's a nice imagery. And we've got a star coming in hot, a normal star, not a neutron star. And that star is going to get squished and stretched and spaghettified by the gravitational well of the black hole. And then, bam, it gets completely disrupted, completely torn apart. Can you pause the video here, actually? Because that's a pretty good image. Amazing. Now you can see some of that material gets flung out, some of it comes back around the black hole, and here they've made it, you would never be able to see the black hole, but you can see that there's a black hole and it's shining. What's shining is not the black hole, it's the material trying to enter the black hole. There is too much star material trying to fall down that well, and there's a traffic jam, basically a space traffic jam. And just like people in traffic jams, things get heated. And if the material gets heated too much, it starts shining very, very bright. That's why we can see them across very distant galaxies. And these, oh, wow, did not expect that. Okay. And the tidal disruption events are very interesting because they allow us to probe black hole physics. Black holes, very difficult to study because you can't make them in a lab, and you can't see them most of the time. But with a tidal disruption event, you can see the type of black holes that you wouldn't otherwise be able to see out in the universe. It allows astronomers to measure their spins, to measure their masses, and to better understand these very weird objects. So the point is that transients, these weird explosions in the sky, allow us to understand many different aspects of the universe. But if we want to learn about these things, the origin of the chemical elements, the expansion of the universe, the weird physics of black holes and neutron stars, we first have to find these objects. And that's not easy. All right, slight change of pace. Can you see the difference between these two images? Yes, I think you will be able to. So these two images are the same image taken by the same phone. They're a very zoomed in, cropped out bit of the image of the Milky Way that I showed you, that I took with my phone back in Chile. Remember that picture at the beginning? The only difference between these two pictures is the file format. This one is the raw image taken by my camera. You can actually see the pixels of my camera. There's some squarey shapes. That's because those are the actual pixels of the camera on my phone. And that's the JPEG saved by the phone. Now, those of you that know JPEG will be very confused because JPEG is a lossy type of file compression. So lossy file format. A JPEG should be worse than the raw image that it JPEG'd. But for some reason, it looks like there's more pixels in this picture than there's pixels in my camera. How is that possible? That's because I have a smart camera. This is a smartphone, and it is using magic maths to artificially increase the resolution of my picture. It's using generative AI. So now that we're halfway through the talk, let's talk about AI. What is artificial intelligence? I'm sure you've seen the word everywhere. I'm sure some of you are tired of hearing it, and to tell you the truth, so am I. Now, in this talk, and I think out into the world, forget the word AI. It's all vibes. There's a long history to the word artificial intelligence that is mostly to do with people being people and less to do with technology. It's interesting, but that's not the point of this talk. AI is just machine learning. I'd go even further. Machine learning is just statistics. Now, I understand that AI sounds a lot cooler than statistics, but sorry, that's what we're doing. We're doing statistics. And in particular, because we're doing learning, we're trying to teach the machine to do something. What we're going to do is we're going to learn a function, a mathematical function. Now, there's going to be no maths in this talk. We're going to use the analogy of a DJ deck. Now, I've never used one of these things. I have no idea how they work, and I don't expect you to either. But the analogy is pretty good, I think. DJ deck, you've got music coming in, a bunch of knobs and dials. If you mess with them, the music that comes out sounds different. That's what a function does. A mathematical function takes an input, mixes it up, something else comes out. Now, the problem here is that we've got our input, we've got a lot of data. we kind of know what the answers are supposed to be, but we've lost the manual. And all of the words are rubbed out on a DJ deck. We don't know how to use this thing. So what we're going to do is that we're going to put stuff in, we're going to play with the knobs and dials until it starts sounding right. That's essentially machine learning. Now, this analogy may be reminiscent of an XKCD that came out 8 or 9 years ago, I believe. If you're not familiar with that webcomic, here it is. So you've got a guy on a pile of maths and another guy looking befuddled saying, this is your machine learning system? Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Well, you just stir the pile until they start looking right. And it is still accurate to this day. That's what it is. That's what AI is. It's a big pile of linear algebra. You don't really understand what's going on now. You just see if it works. Now, obviously, there is a method to this madness, but that's the best way to demystify AI that I know. Now, artificial intelligence versus machine learning, honestly, just vibes. The way that I would put it is I think people are very happy to call something AI if you're teaching the machine to do something they didn't think machines could do. But eventually, machines can do the things and we get used to it. And I think a very good example of something that would have been called AI back in the day, but that we now take for granted, is computer vision. You take it for granted that Facebook can recognize your nan's face in family pictures. You take it for granted that a camera on the highway can take a picture of your car, read the number plate, and send you a fine automatically. But a couple of decades ago, computer vision was the stuff of sci-fi. It's the stuff you would see in movies. People would walk into a futuristic looking building. There's a fancy door that scans your eyes, scans your face, and then the door opens like magic. I can open my phone with my face. No one bats an eye. So what happened? Well, computer vision started getting good in the 90s. Actually, convolutional neural networks came out in 1989. Now, we're going to use that word a couple times, convolutional neural networks. I'm not going to explain how they work, because that would take half a semester of an undergraduate degree. We don't have that kind of time. But all you need to know is convolutional means a fancy filter. You apply a filter to a picture, and neural network is just a mathematical function that's going to make the decision. So in the 1990s, convolutional neural networks became able to recognize handwritten digits. And here you've got an original Yann LeCun. Yann LeCun is the guy who came up with CNNs. I nicked that off his website. I don't know if it's copyrighted, but here it is. And the reason it looks like this is because it's genuinely from the late 90s and it's still, I think, one of the best representations of how CNNs work. You can see here the handwritten digits scrolling through. And here you can see how the first layer of filters affects the pictures. Some filters make some edges look more prominent. Some filters make the body look more prominent. That's pretty sensible. You understand what's going on. Now, in the second layer of filtering, things look messier. As humans, we can barely recognize the numbers. And by the final level of filtering, things are completely abstract to the human eye. But those features, these abstractions, are what helps the computer actually understand the digits. Now, computer vision had a bit of a lull in the 2000s, but then got really, really good to the level of it's not sci-fi anymore in the 2010s. The ImageNet dataset was 1.2 million images, labeled images that were released out into the world. And then they said, okay, take the pictures and make your algorithms, and then we'll put you up in the challenge against humans and see if your computer can do better than the humans. By 2011, we had the first neural network that could beat the humans. By 2012, we had the famous AlexNet that won the competition by a very, very large margin, so much so that it helped accelerate what we now call the deep learning revolution. And then in 2013, we had a lot of tech giants like Facebook hopping on the trend. The reason that I'm highlighting Facebook in particular is because they called their thing the AI lab. Now, artificial intelligence up till that point was not, crackpot word, but like it It was a very overused word in the late 20th century, so people didn't like using that word. And basically, Facebook reclaimed AI, and that's why 10 years later we're all talking about AI and not machine learning. It's because of this. Now, what was special about AlexNet that kind of started this revolution? Well, it was just massive. The thing that recognizes the handwritten digits, the Net5, it has 60,000 of these knobs and dials in the function. AlexNet has 60 million. Basically, what these people showed is if you just throw a lot of computational power at something, the machine can do a decent job. And that's essentially the story of advances in machine learning in the last few decades. The breakthroughs come when you have more data and more compute. And for computer vision, the 2010s was just the perfect storm. You had more data, all of the data you needed, because by the end of the 2000s, we were all on social media. We all had cameras in our pockets. We're taking pictures of our faces and posting them online. The compute came because GPUs were extremely widely available or becoming widely available because of the CGI and video game industry. These are important because they're good at linear algebra. Remember the guy standing on the pile stirring it? Linear algebra is the thing you do when you're training a machine. So what that means for astronomers, going back to the astronomy of it all, is that by the early 2010s, 2015, it was not sci-fi to teach a computer to recognize images and to classify them. And that's very useful if all you do all day long is manage images. Now, can you spot the difference? Maybe, we'll see. I don't know how well you can see from, let me see from a distance. Yeah, maybe. Can you spot the difference between these two pictures? That's the before, that's the after. Look in the middle. There's a bit of a difference. I'm going to help you out. There's a bit of a fuzzy thing there. So I'm going to remove that, and bam, there is the supernova. See it? Right there. If you see it in the, there's the little bit of a dot. It's hard to see, isn't it? Tough job. This is all we do with our telescopes. It's called difference imaging. You take a wallpaper or reference, you take an observation, you subtract one from the other, and bam, you can see your supernova. But the sky is big, and difference imaging is not easy. Difference imaging often goes wrong. There's no difference in these two pictures, but it's a very crowded field, very difficult to align, very difficult to remove. There's a lot of apparent sources in this difference image, but none of that is real. So we've got a bit of a needle in the haystack problem with our surveys that look at the sky over and over again. We've got tens of millions of these differences, but only a handful of real interesting explosions that we care about. So that means we have to automate, and the computer is going to help us. Now, the first thing we're going to do is not machine learning, actually. The first thing we're going to do with our massive alert stream of tens of millions of differences is some basic quality cuts, the details of which I'm not going to go into. But that removes a whole bulk of crap. The second thing we're going to do is cross-matching with astrophysical catalog, so we can remove the known variables. To put that into practice, if I'm an astronomer that cares about explosions in distant galaxies, I don't want to find Betelgeuse every night, right? So I can cross-reference that and remove it from the stream. But once you've done this, you still have tens of thousands of potential alerts, many of which are what we call bogus. And that's where the CNN, the convolutional neural network, comes in really handy. So we've got a CNN in Atlas. Every single sky survey has a CNN these days. And in our case, we take the difference image, the center of the difference image, we put it through our CNN, filtering, 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 decision, decision, decision. And what comes out is a number between 0 and 1. That's the real bogus score. 0 is bogus, so not real. 1 is real. And everything below a certain threshold gets garbaged. This is very powerful and can remove 98.5% of the garbage in our stream. It makes us go from tens of thousands of potential differences to a few hundred. And then that gets eyeballed by people. A few hundred is still quite a bit. And eyeballing is not an easy task. It's a pretty tedious task. In the eyeballing list, when I arrived in the team, 85% of the alerts would be essentially garbage, right? And half of the rest would be good stuff that we care about. Not the kilonovae, there's not many of them. And then the rest would be real galactic stuff, because there's explosions in the galaxy as well. So it's very time consuming. But the reason it's so hard to automate is because humans are just really good at complex pattern recognition, and it is not easy for computers to do this. Eyeballing requires looking at a web page like this. So you do have the before, after, and difference image, just like the CNN was looking at. But you also have information about the light of the object. Was there any previous detections or only non-detections? Do they look spurious? Do they look sus, or do they look real? There's the coordinates on the sky. Is it near the galactic plane or near a known object? Is there a galaxy nearby, right, near that alert? How far from that galaxy is it? Do we know the distance to the galaxy? Do we know if the object is coincident with the center of the galaxy? This information requires expertise to make a good decision, but more to the point, it's just a lot of varied types of information. You've got the images, that's what the CNN looks at, but all of the rest is important. And you've got words, and you've got numbers, and you've got ordered numbers. So you need the machine to be able to look at all of these at once if it wants to make decisions similar to the human. And my job was to create this thing. That's what I wanted to create, is something I call the virtual research assistant, which sounds really fancy, but it's just a bot. The point is, it's trying to do eyeballing before the humans do the eyeballing to save them time. So the virtual research assistant ranks the eyeball list and then crops the crap. That's it. That's it, but it's not easy. Ranks the eyeball list like the humans would, and then crops the crap. And with this, I've managed to, I don't know if you can see that number, we've gone from hundreds of alerts a day to tens of alerts a day. The VRA has been working in production since September, and we're saving between 70 and 88% of the time of the eyeballers. Now, there's a lot of numbers on here because these are actually the technical plots that I send the team, but I just want you to focus on the gray area, the gray fraction. That's the fraction of alerts in a week that get handled automatically by the VRA and that humans don't have to touch. That's the amount of time saved, essentially. And as you can see, it ranges from week to week, but it's in the 80s in general. Sometimes there's a problem with the telescope and we have to go back and fix it. And it changes based on weather, but we're around 80% time saved. And that's the first prototype. This one was supposed to be bad. So I'm quite happy that this is working so well. Now, how does that work? Well, it's the same story. We're training a function. The inputs are what I was describing. We've got location on the sky, light of history. We're using the CNN score. You know, we've already done the computer vision. We're not going to put that in the bin. We're going to use it. And the outputs are going to mimic the kind of decisions that the humans are making when they're eyeballing. When we're eyeballing, we ask ourselves two questions. One, does it look real? Two, does it look like it happened in this galaxy or in another? And that's what the function is going to give us. Now, without going into the details, I'm going to try and give you an analogy for what how my function is trained. Because I'm not using a neural network, I'm using a little mathematical trick called gradient boosting. Now, gradient boosting is a very neat little mathematical trick that statisticians came up with a while ago. And the concept is this: instead of trying to train a massive function, use a big DJ deck with loads of knobs and switches and all that, we're going to start with a very small function, very few knobs to train. And that function is going to be really bad. It's going to do a terrible job, but we're just going to run with it. And then we're going to take the results, look at how bad they look, and we're going to train another little function that's going to make them a little less bad. Still going to be bad, but it's going to be less bad. And then we're going to train another little function, another little function, etc., etc., etc. And so this collection of little functions eventually make decisions that are not that dumb, that are actually pretty good, and they can be trained with relatively few examples compared to neural networks. So what do we get in practice? In practice, we get a graph like this. we get our real scores from 0 to 1, our galactic scores from 0 to 1. And here I've color-coded things similarly to the previous plots. The blue stuff is the stuff that I care about. Those are the extragalactic explosions labeled by the humans. And as you can see, they're piling up really nicely in the real corner and the extragalactic or not galactic corner of the plot, which is great. That's exactly what we wanted. But actually what we were trying to do was rank the eyeball list. So how do you go from 2 numbers to 1 number that ranks the list? Well, we're going to use the really fancy, really newfangled technology of the Pythagoras theorem. 2,500 years old and still kicking. We're going to do a geometric distance. We're going to say this part of the plot is the best part of the plot. You know, it's the most real, most extragalactic. And we're going to rank everything with respect to this. If I've got an alert and this is its location on the graph, I just calculate its distance to that corner. It's a squared plus b squared equals c squared. And that's it. And that works. So maybe I should amend the statement I made earlier. Discovery is actually a partnership between researchers and the right technology. That technology does not have to be new. You can use really old technology and it can still do the trick. Right, so now this talk could end here. I believe this is 50 minutes. I've not been counting. But the reason that this talk is an hour and not 50 minutes is because there was AI in the title of my talk, and I have not yet mentioned ChatGPT. And I am sure some people are itching. What about large language models? So we're going to mention large language models. We're going to mention generative AI. We're going to have a little conversation because I don't think there's enough nuance in media about these things. And I want to look at it from the point of view of a scientist. You know, how do we look at these new technologies and what they can do for us? So can you tell what this is? Maybe people at the back. It's a bunch of squiggles mostly. This is a zoomed in cropped out bit of a bigger picture that I took with this very phone, the same phone that took the amazing picture of the sky. This is a announcement board in an airport. I was stuck in Venice for 7 hours and I was trying to check how late my plane was going to be. And because I can't be bothered and I am blind, I was taking a picture with my phone and hoped to zoom in to see better, and oh, my phone had turned the words into squiggles. Now, to understand how this might happen, we're going to take a little detour and go back to 2016, when we reach another milestone of machine learning, when DeepMind's AlphaGo beat Lee Sedol, the world champion at the game Go. Now, this was a big deal because Go is much harder to train computers on than chess, and it was the first time it was ever done. But AlphaGo won 4 games, not 5. Lee managed to win one of the games, and he did that because he made a move that AlphaGo did not expect, and it made the machine completely misbehave. It started to make terrible decisions because it was put in a position that it had never encountered before. We can think of learning a function and exploring how these dials like change our answers, change our inputs, kind of like exploring a map. This is a screenshot of the game Civilization 5, in case you're not familiar. And in Civilization 5, you explore a map, amongst other things, and the bits of the map you've not explored are covered in what we call the fog of war. And essentially, when you're learning a function as a machine, what you're doing is trying to lift the fog of war in as many areas as possible. But the problem is you can't do that. You can't lift the fog of war everywhere. The more parameters you have, the bigger the map, exponentially bigger. It's something called the curse of dimensionality. So the more areas of fog there's going to be. And if you fall into one of those areas of fog, then the machine doesn't know how to behave. That's what Professor Neil Lawrence calls Sedolian voids, in honor of Lee Sedol, who put AlphaGo in one of these voids. And these Sedolian voids are a problem. They're the reason that this happened, because my phone, I imagine, I don't work at Google, I don't know how they actually did it, but my guess is that my phone and the software in it that's made to make the pictures have a artificially higher resolution is trained to make landscapes look better, to make your face look better. But the details of your face and landscapes don't have right angles and straight lines like those words. So the machine saw the straight lines and right angles and tried to smooth them out to make them look better. But then it completely scrambled the only piece of information I was actually after. That's a problem if what you care about is the weirdest, rarest stuff in the universe. Because if you care about the weird, if you care about the rare, you're more likely to put your machine into one of these Sidolian voids. And if you're using machines that have really gigantic parameter spaces that are very difficult to explore, that's an issue. Now, the other problem with generative AI, this is a problem with everything in general, but it's just that Gen AI has massive parameter spaces that are very difficult to keep track of. Generative AI is probabilistic. And what that means in statistics is that if you put something in and you do it again and again and again, the output's going to be different every time. A little bit different or a lot different, it depends. But that's an issue. The other issue is things like large language models were created and designed to sound like humans. That's their job. Their job is not to know the difference between right and wrong, to know what truth is. That is not how they were trained. It's very difficult. If you think about how would you test that something is true or trying to tell the truth all the time, it's a very difficult thing to even test. So we're not even going to go here today, but the point is that's what they were trained to do, sound human, not tell the truth. These two issues are particular challenges if you're trying to do something that's reproducible. And as a scientist, that is the pillar of what I do. It doesn't matter if I do something that looks cool, if I can't reproduce it 100%, that is not science. Reproducibility is key in everything that we do. So to go back to this statement, earlier I said that progress is a partnership between researchers and the right technology, because the right technology at the time was not new. What I want to emphasize here is that new technology is not necessarily right. Just because it's new does not mean that it's going to lead to new discoveries. New technologies bring opportunities, the opportunity for new discovery, but new discoveries are not an inevitability. We have to try them out, test them out, and be very skeptical, very careful with what we do. There is a whirlwind of hype around AI, and it is not just in the general media, it's not just in public audiences, it's also happening in science. And I fear that we're creating a lot of stuff that is not as reproducible as it should be. We need to be as skeptical as we are passionate of these new technologies. Now, it sounds like I hate ChatGPT. That is not true. I do use it. I use Copilot to code all the time. But I want us to take pause and try these things out before we decide that they are going to lead to progress in all sciences. So what is the right technology when we're doing our jobs? The right technology is understandable, it's reproducible, and I would like to also add that it should be sustainable. Now, I'm only going to touch on this very briefly because it is not my job and I am not educated enough to talk about sustainability in great detail, but remember that machine learning breakthroughs came up because there was more data and more compute available. More data and more compute comes at a cost. It seems like it's free because it's in the ether and you don't have to handle it, but more data and more compute require more energy, they require more resources, they need to be dug up from the ground, that have a human cost and an environmental cost. And I really want us to be mindful of the planet that we're on, even when we're looking up at the heavens. All right, so to finish this, I'm going to say a couple of thank yous. Thank you to Ken Smith, who is the server wizard that keeps Atlas afloat all day, every day, even on weekends, and he's been my partner in coding crime. Thank you to my mentors, Stephen Smart and Stephen Roberts, especially Stephen Smart, because I wouldn't be here today without him. It was very, very tricky to get this job. 10 grant rejections, a year and a half not knowing what my next gig was going to be, and he believed in me when I didn't anymore. A big thanks to the Herschel Society for the prize, and also a big thanks to you all for being here tonight.
Questions? Stand.
Shout.
Very skeptical. Charles is looking very skeptically at me. What I mean, I don't know if I can frame it as a question, but as you were doing the talk, I was writing down a series of questions, and during the talk, they were all being answered.
Oh, thank you. It's like there's a plot or something. Oh.
But one of the questions I put down right at the beginning has come back at the end.
Yeah.
Which is really to do with the, when you started off with taking photographs of the heavens with your mobile phone,
Mm-hmm.
and the binary star being sort of attracted to the black hole,
Mm-hmm.
was giving off a bright light.
Yes.
So my question started off, series of questions started off by asking, why was what was causing the radiation? But in the end, my last question was something I'd asked in the middle, which is, it is a probabilistic thing. I mean, it is a system that is under sort of test, if you like, whether this finding the right solution will happen. So it's probabilistic. So my question was, how probabilistic is it that what we're observing and using AI to make more, shall I say, more real,
Mm-hmm.
is actually doing its job?
Okay, so two very good questions. First, where does the light come from when you have a merger or an explosion? The light, the optical light, the one that you can see, the one that I study, almost always comes from things being really hot. Now, how do they get hot? Nuclear decay. So they make all of these new elements, and then they're really, really unstable. And as they decay, they produce photons, they emit light, and this is what we can see. Now, about how can we test probabilistic systems when we're doing stuff like this? So probabilistic systems, a model being probabilistic has a very specific definition. It means that the answer that comes out is not one number that's the same every time. So 2 + 3 = 4, not probabilistic. You can use it in probability, but that in itself, that construction, not probabilistic. Probabilistic would be if you're drawing a random human from a room, you know that they're going to be between like 4 foot and 7 foot. They're never going to be 12 foot. You know that. But they're going to be in a range of solutions, and you don't know exactly where that is. So that's what probabilistic is. Now, the kind of stuff that I do is not probabilistic by design, because I don't need to, and I don't want to. I like knowing that my answers are going to be the same every time. Now, that being said, it's a very complicated topic in general. Probabilistic models have different uses. So sometimes you're going to have to use a probabilistic model, and your tests have to be representative of what you might see in the telescope, and you can only be so sure that things are going to behave this way. So the answer is not very satisfactory. It's a lot of like basically, I don't know if I can say it like this, fucking around and finding out. Sorry, but that's what it is. But the way I would put it is, If you don't have to use a probabilistic or a complicated model, don't. If you don't have to use machine learning, don't. That machine learning should be the very last thing that you do when nothing else has worked. And within machine learning, a probabilistic model should be the very last thing that you try when nothing else has worked. Keep it simple. If you can use Pythagoras, just use Pythagoras. Yeah.
Applying this to imaging.
Mm-hmm.
So how can we how sure can we be that the imaging that the the use of AI is producing is close to the truth?
Okay, so I should really emphasize, my phone uses AI to make more pixels. We do not use this in astronomy. Never, ever, ever. For the love of God, absolutely not. Because generative AI basically generates data. That's cool if you're trying to make a picture look nicer. Terrible if you're trying to do science, because you want your data as raw from the universe as possible. So it was an example with my phone and a picture on the theme of astronomy. We never use generative AI in astronomy pictures. Let's move on to someone else maybe, and we can talk afterwards. Yeah.
Many of these, sorry, how many of those, I can't remember quite what you called them, the neutron stars hitting neutron stars.
The kilonova.
How many of those events do you find each week?
We've got 3 total. We've got 3 in total. These are so hard to find because they go up within a few hours and then they start going down really, really quickly. They're fainter. They're also rarer. The first one that we found back in 2017, the first one for sure, we found because the gravitational waves like arrived on Earth beforehand. And so people heard the gravitational waves and then they were like, okay, something happened. Point somewhere in this direction, and then people found the optical light a few hours later. So at the moment we have 3, and they're always found because something else happens, either gravitational waves or a burst of gamma rays that comes from that disk that's basically shooting a space laser at us.
Just following on, how many supernovae?
Thousands. Now it depends on the supernova. Some of the boring ones, thousands. Some of the exciting ones, like 12. Like I said, there's many subtypes, but we've got thousands. TDEs, it's 100. Tidal disruption events. The hungry black hole that spaghettifies a star, that's 100.
Another question. Over there.
Thank you for that talk. It was really fantastic presentation. The fact that we only have so few of these events, and even the 3 for the kilonova, is fairly optimistic given the quality of the other ones. How much of a problem is that training your data sets, both for your virtual assistant and your network?
Absolutely. The reason the virtual research assistant asks such basic questions like the eyeballers is because so many people, I don't want to say it, bless their heart. So many people have created transient classifiers that try and classify 12 different things, some of which we have no known examples. They only use models to train the algorithms. And I don't think that is realistic at all. So the virtual research assistant asks 2 very basic questions. One, does it look real? One, does it look extragalactic? Now, a kilonova, that's the thing that annoys me the most in the astronomy transient my community, is people will train things on kilonova, supernova, etc., but they will forget that cataclysmic variables are a thing. What is a cataclysmic variable? You'll say it's a type of explosion that happens in this galaxy. And these explosions are quite quick, very, very similar looking to kilonovae. They're a very good contaminant of kilonovae. So if you don't take them into account, where's my plot? So that's why you've got the extragalactic stuff and the galactic stuff here. Now you may notice this axis is longer than this one. In my actual algorithm, where I use Pythagoras, this axis is much longer. That's because I want things at the top of the list to include the extragalactic transients, but also some of the galactic ones, because these are very good contaminants of the stuff I care about. So I want these things to be, these false positives that are actually decent positives, to be at the top of the list. So if there's something like a kilonova that I don't have a lot of good examples of and that could masquerade as one of these yellow things, I don't want to miss it. So I'm putting that in a similar sort of pot. So you're right, if you don't have a lot of examples of something, very difficult to train on it. And so you have to be careful with your metrics. What are the metrics that you're using to assess the model? And do you risk missing out on the things you truly care about? Does that answer the question?
Another question.
Hi, that was a really good talk. Thank you. When I was on placement, I was in biomedical research and doing image analysis. So I thought what was really good about this is a lot of the similar topics came up, even though very completely different scales. But I suppose for a computer, it doesn't matter if the object is a galaxy or a nuclear pore, a blob's a blob, and it's just numbers.
A blob's a blob. I'm stealing this.
But I think a big problem, which both in biomedicine and astronomy that I've seen come up, is how big data is getting, especially with multi-dimensional data. You say you're imaging across time, that's the same with, I don't know, plant samples. So I just wanted to ask about how in astronomy you're balancing or like managing this big data, because you also mentioned the issue of sustainability. So what are you doing to counteract sort of people's philosophy of get as much data as possible and as much information as possible, because you do have to make sacrifices with that?
Yeah, that's such a great question, because you're balancing the fact that managing a lot of data is complicated, but also the anxiety of reproducibility. If I delete my data and it's gone forever, what if I delete something and it was interesting? So what we do in Atlas is that we will, and when I say we, I mean Ken, the wizard, will regularly clean the database and remove information related specifically to the garbage data, because there's so much garbage. And so keeping that at, indefinitely is not manageable for the server. So we'll do that every 6 months. I think that's the hope, and that helps a bit. I think this is going to be mostly a big problem in the era of Vera Rubin, which I didn't touch on in this talk, because they're going to have so much more data, and I don't know exactly what they're doing other than making big data centers. The radio people are in an awful lot more trouble with SKO, because that's exabytes of data. Like, they're in such trouble, they can't even get the data off the telescopes to do the analysis. They have to do the data reduction at the telescopes because the internet is not fast enough. They don't have enough internet. That's how bad it is. As someone who's not an engineer, unfortunately, I don't have a satisfactory answer. I'm the kind of person that creates models. And so my philosophy is, if I can make something as dumb as an Excel spreadsheet and it works, I'm going to use an Excel spreadsheet. But the data engineering is such a big problem. And I think it kind of touches on the fact that science, the way that we look at science is very outdated, because science is truly done not just by a scientist, but you need a scientist, you need a data engineer, you need a DevOps, you need a developer, you need a machine learning engineer. You genuinely need these people to do things like astronomy, to do things like medical imaging. And we're going to have, and when I say we, I mean the people in power are going to have to do something to keep teams that interdisciplinary working on these projects long term, because otherwise we're not going to be able to do it.
Thank you.
Another question. There's one up there. Yeah.
I'm probably going to butcher this question a little bit, but in terms of the actual eyeballs, that pattern recognition that people have, that's based on their experience and the amount of time they've put in. As stuff like this becomes inevitably used and more popular for all the reasons that you've listed, Do we lose that expertise in 50, 100 years?
Such a great question. Yes, that is such a great question that has come up a couple of times with other interdisciplinary colleagues. I think that's true at every age, not just with AI. Like, I can't do analytical maths the way that an astronomer in the 50s could. I'm basically shit at maths, right? If I can't do arithmetic the way that an astronomer would in the 1950s, because I have a calculator in my pocket, literally. So yes, there is some expertise that will be lost, and it is something that worries me. I think it's something we need to, on the one hand, not be too scared of, but on the other hand, we need to not bury our head in the sand. We need some people to maintain that expertise, but we don't need everyone in the team to be an excellent eyeballer. So now, in the case of eyeballing and things like that, I don't think we should remove the human element ever. So I don't think that expertise will be completely lost, because you need a human to do the final decision making, especially if you're going to be triggering expensive telescopes that cost £10,000 a night. You don't want a machine to be making that decision. You don't want a machine to be binning the interesting objects. So the other problem is, how do you handle the human-machine interaction? So that's another expertise that needs to be built that doesn't necessarily exist yet. Because the problem is, people are tired and people are overworked. If they see the machine saying that looks good, they might be like, fuck it, like, looks good to me too, bro, and they're not going to look too hard. We need to fight that. I don't know how to yet. It's something I'm going to look out and explore, but there is the case of astronomy expertise. We don't want brain drain to occur, and understanding how these machines work so that we can make good decisions always. Yeah?
Another question. Actually, I've got one. If you go back to the process you were describing, whereby you have a sort of huge set of data, and you're eliminating various elements of it on the way through to get rid of.
You mean this one?
Yes. And you rely on the last stage to be done by a machine. How can you be sure that machine will be reliable the way it does that?
Well, that's what I'm saying. We shouldn't remove the human. I generally don't think. Some people in astronomy are like, ooh, we can basically have RoboCop writing papers for us. I think it's a terrible idea. I think it defeats the point of science. If we're going to have robots writing papers and robots reading paper, then what are we doing? But more to the point, I think the very last bit of decision making, because of these things I was talking about, these Sidolian voyage, the fact that rare, weird things make machines behave erratically sometimes. The way I approach this is, I want my machine to let through the weird stuff and basically not make a call. And then say to the human, you do this. I don't know how to do this. You handle that. And that's what the humans are for. The machine will do as much of the easy stuff as possible. And then the humans with their expertise and you know, they're just going to make a decision. It might not be the right one, but they're going to have a reason for it, and then they can answer for it in meetings. There's also the question of accountability, you know, who's accountable for a crappy decision if you have computers all the way through. So you can't be sure that a computer is going to make the correct decision 100% of the time. And when you think they're going to make more bad decisions, that's where I think you need to put the human back in.
But if it decides to exclude something, then the enable never sees it.
That's true. That's true. And that's why you need to test your algorithms to see what they exclude. And that's what we do in the VRA. Where do you have these fractions? I have checked what the VRA binned that other telescopes detected and put out in the transient name server, we call it. And I checked, were these bad calls or were they good calls? And most of the time, they were really good calls. We didn't put stuff that were cross-matched were either false positives that people were a little too excited about, but turned out to be galactic, so not real. And some things were real, but not visible by Atlas. It's just that the other telescope can see half a magnitude fainter than us. and it looks like genuine garbage in our data. So you can't expect, a human would not be able to tell. You can't expect the machine to tell. You can't outcompute bad data. I will just put this out there. Just because you have a fancy algorithm doesn't mean that it creates new information. So it is a concern. We do check.
Another question. Yes, sir. Wait, please wait, please wait.
Yes, I'm not sure I understand why a supernova that occurs in galactic is different. It should be so different from a supernova that occurs outside the galaxy.
Yes, yes. So I should have explained that better. These are not supernovae. If there was a galactic supernova, you would know. First of all, the galactic supernova people and the neutrino people will be all over the place. They talk about the galactic supernova like it's the second coming of Jesus. But these things are explosions that are not these really crazy ones I was talking about. They're cataclysmic variables. These are explosions, small scale. They're stars that go into outbursts, things like that. So interesting, but not for us. Does that answer the question? Not regularly enough. So our galaxy has a supernova rate of 2 per century. So the question was, is there no supernovae that occur in our galaxy? The answer is not regularly. 2 per century is the current going rate. There was one that wasn't even visible from Earth back in the 18th century or 19th century. The last one that was observable from the Earth was Tycho's supernova in 16 something, can't remember, or 15 something. And the reason is that the galaxy, I don't know if I'm going to be able to scroll that far back, but remember the galactic plane with the big clouds? You can't see things behind the clouds, essentially. They're really, really obscured.
Some of us have hopes of Betelgeuse, but it might be a long wait. Another question. Yes, sir, out there.
Thank you. There's a lot of work involving laboratory astrophysics where you're recreating conditions such as the inside of a star. Would this alternative area of like observing the night sky help with the sustainability or reproducibility issues in the astronomical community?
So not really, because there's not much you can do in the lab. So I know some of the stuff you're talking about. I know about some of the stuff that's done in labs is basically fluid dynamics and their approximations to the kind of fluid dynamics that might be happening inside the stars. So to an extent, yes, because it means that maybe some people don't have to run really expensive simulations, and simulations are expensive, even if there's no AI in it. Sometimes AI can make simulations cheaper. So, you know, AI can be good for sustainability. So I know what you're talking about. I think it has a very limited range of applications. Now, the applications it can be applied to is very useful because it means you can actually touch the thing. But I'm sure the people in these areas would have, you know, plenty of caveats to add to this, because if you're playing with a liquid in a lab that is room temperature or even slightly hotter or cooler, it's not the same as a plasma that is 10 million degrees. So not really, but it's really cool science.
Thank you.
Another question. If there are no more, I have actually, there's one down there. Yeah.
Oh no, did I insult an astro lab person?
Oh no, not at all. No, on the contrary, I'm quite pleased with your view, for example, on AI. It's very clear-eyed. Students take note. Now, the question I had actually was that you referred to the Atlas survey. Your work was in the context of Atlas, which was for near-Earth objects, not necessarily the stuff you were after. So the interesting question from my perspective then is, how well does your lab assistant, for example, map to other surveys? Are there big hurdles, or does it really just translate quite well?
So that's a very good question. So it does something like this. Can this apply out the box to other surveys? The answer is not out the box, because the training data is specifically, So I'm just going back to this plot because that's the test data, but the test data and the train data are from the same sample. The sample was me gathering human decisions on the Atlas data between the end of March this year and the end of August this year. So very specifically looking at, and I'll go back to this, very specifically looking at these kinds of numbers that come out in the actual alert stream of Atlas. So in another alert stream, some things would be the same, like the coordinates, but other things would be different. The cadence would be different, so the numbers, the features I extract from Lycos would be different. Now the advantage is the VRA being trained with histogram-based gradient-boosted classifier only needs a few thousand samples to be trained. It's not like a neural network. My philosophy is trying to make a general thing that works on everything is the best way to make something that works on nothing at all. So I work with the data that comes exactly in production. Most of the VRA code is very specific to Atlas. What is applicable is the whole methodology of how do you develop something like this, all of the questions that need to be asked. And I got a little bit of money from the Royal Society, woo, £6,000 to go to France and bring some French people over here to start making a VRA for the Think broker for the era of LSST. So it has to be designed for Think, but the whole methodology and philosophy is kind of the hardest thing to get off the ground and see if it actually works.
Okay, any more? If not, I have one question online, which I will put to you, but I think those of us who've been listening for the first hour could answer the question for you. What inspired you to pursue physics?
Oh, I like exploding things. Shiny, it's so pretty. I like understanding how the world works. I was the kind of sad little kid who would watch documentaries about black holes. Yeah, it's just pretty cool. I wasn't the kind of person that did a lot of maths. I'm trying to find a pretty picture to end on. Yeah, this pretty picture. And so I wasn't in it for the physics. I was in it for the astrophysics. So the physics, I like to understand how the world works, but frankly, circuit boards bore me to tears. I wanted to know how black holes worked and how supernovae exploded. Yeah, documentaries as a child.
Héloïse, you had a fascinating topic and a brilliant lecture, which produced some very stimulating questions and some very good discussion. So please join me in thanking Héloïse for her wonderful talk.
Thank you.